All right, hello everybody. We are on the clock. I wrote your exam and it's got questions on terpenes on it, so I need to prepare you for those questions. We probably will get to most of terpenes today, but probably not all of it. And I'll make sure that you're able to do what you need to do on the exam based on what we talk about today. So, what do you need to know about terpenes? Well, first let me draw a few for you. These are generally non-polar natural products. They are made in plants and in animals, so it sort of depends. Most of the ones we talk about today will be from plants. Some of them have interesting flavors and smells. Others have interesting medicinal properties. They all have a core structure in common that you will need to learn to recognize. So here is a simple terpene. This is called limonene, and it smells like citrus. There is a stereocenter in there. I'm not showing you what the configuration of the stereocenter is. For terpenes, we will mostly be concerned with connectivity rather than stereochemistry. This one is called menthol, essential oil of peppermint, and in various forms it can have a cooling effect on skin. This one is a relative of limonene. It doesn't look like it to begin with, and you're actually going to despise me for what I'm doing now. There's a carbon in the middle there that's bonded to two methyl groups, and it's also bonded to these carbons, so that's a 4-membered ring. If you want to see what this looks like in a more physically realistic arrangement, you could draw a sort of pseudo chair like this, and then put the carbon here, down here, 2 methyl groups, and then there's a 1, 2, 3, 4-membered ring. That's called alpha pinene, and it's a component of pine oil or pine resin. And if the double bond were here with the methyl group, it would be beta pinene. And we could draw a ton more molecules, though hopefully you're getting the point. Here is a relative of these molecules that's much less complicated. This is called geraniol and can be isolated from roses. All of these are 10 carbons, and you'll find that with terpenes, the number of carbons comes in multiples of 5. So all of these 10 carbon terpenes are called monoterpenes. A terpene technically then has 10 carbons, and they are comprised of 2 5-carbon, what we're going to call isoprene units. What do we mean by isoprene? Isoprene itself is the following alkene. An isoprene unit is a network of 5 carbons that follow that basic pattern, 4 carbons in a row and a branching point on the second carbon. That is an isoprene unit. And one of the skills you're going to need to be able to get from all of this, remember our theme is the relationship between structure and function. So one of the skills you're going to need to be able to have is to look at a terpene and identify where the isoprene units are. To do that, it's helpful to number the carbons in an isoprene unit, and you can choose whatever numbering scheme you want, though because I am in charge, we'll choose mine. 1, 2, branching carbon 3, 4, and 5. Now please do not tell me that according to IU-PAC rules, you should count 1, 2, 3, 4, and then the methyl group can be a substituent on carbon 2. I know that, I also don't care. And it's helpful actually to put the methyl group at 3 so that you remember it's always branching off carbon 2. The key to identifying isoprene units in organic molecules is finding those branching methyl groups. Okay? Now, when looking for isoprene units in a terpene, you ignore the pi bonds and you ignore anything that's not carbon. You focus exclusively on the network of sigma bonds. Let's start with geraniol, which is the simplest terpene that I've listed here. And let's see if we can identify isoprene units. The easiest place to start is the branching methyl groups. So that's carbon 3 of one isoprene unit. That's carbon 3 of another isoprene unit. Now from here on out, choosing which are 1, 2, and 4, and 5 gets pretty straightforward. You can get it wrong, but if you're paying attention, you won't. The carbon that's bonded to 3 is 2. That's easy. And then you have to pick one of the two that's bonded to 2 to be 1, and the other one to be 4, right? If I chose this one as 4, I got a problem because there's no place for 5, right? So that means this is 1, 1, 2, 3, and then that makes this 4 and 5. And then, again, this would be 1, 2, 3, 4, and 5. Those are the two isoprene units, the orange isoprene unit and the purple isoprene unit that are in geraniol. And you'll notice that there is a sigma bond, which I'll highlight in red, in between those two isoprene units. Okay? Let's do some more with the rest of the terpene products. Before we do that, I want to point out we're going to not only talk about analyzing terpene structure, but we're going to be able to do mechanisms with terpene-like molecules. And to set this up, I need to point out that there is a linear precursor to all of these 4 terpene or 3 terpene products that I drew. And I'll draw that for you right now. This is called geranyl pyrophosphate. I don't generally ask questions on my exams, which of the following is geranyl pyrophosphate, so it's not really necessarily worth memorizing terpene names. But I'll tend to use them a little bit in class, so it's helpful if you know enough or are familiar enough that you can follow along. Geranyl pyrophosphate is the monoterpene linear precursor to all of these other terpenes. And you can see that geranyl pyrophosphate shares the same basic arrangement of isoprene units as does geraniol. That is, you have 1, 2, 3, 4, and 5 for the orange isoprene unit, then 1, 2, 3, 4, and 5 for the purple isoprene unit, with a bond between the two isoprene units, okay? And it turns out that the pyrophosphate group here, I can't remember whether you've seen that before. I think you have when we talked about ATP. This is a good leaving group. And later on when we do mechanisms with terpenes, that good leaving group is going to be really important. Notice about this good leaving group that it's at a carbon that's adjacent to a pi bond. This is not only just a good leaving group, it is an allylic good leaving group. So you expect this kind of molecule to do SN1 type chemistry where the leaving group leaves to give what's going to be called a resonance stabilized allylic carbocation. So that's just a preview of some of the chemistry that we're going to be doing. Before we do that though, let's identify isoprene units in, say, limonene and see whether we can figure out where the methyl groups are and where the bonds are between two isoprene units. Yes?
Do you ever have like the carbon 5 of the yellow isoprene unit on into carbon 5 of the purple isoprene unit?
Right, good question. Yeah, I'm glad you asked that. Notice that in this, both geraniol and in this linear precursor, it's orange carbon 5 that's bonded to purple carbon 1. It's helpful just to introduce some terms to talk about terpenes and isoprene units in sort of head to tail fashion. So I'm going to call carbon 1 the head and carbon 5 the tail. And you can see that in this linear precursor, you've got head to tail linkages, the red line, between isoprene units. Your question is, do we ever see tail to tail or head to head linkages? The answer is yes. They can be somewhat difficult to do, but they do show up. Yeah. Not in the linear precursors, though. The linear precursors are always head to tail for reasons that I'll show you. Okay, what else? Am I recording? That is a good question. Yes, we are recording and we are capturing audio, so that is a win for today. Yay. Feeling great about life. Okay, for now. So let's identify the branch. Yes?
Will we ever get linkages off of that carbon 3 carbon?
Do you ever get linkages off the methyl group? Not usually. Which is why the methyl group is key to identifying where the isoprene units are. So let's look at limonene. This is carbon 3. That makes this carbon 2. There's also a branching methyl group here. We'll call that carbon 3. That makes this one 2. That one better be 1. Okay, with me so far? So the one that's bonded to 2 here has to be 4. Now, I got a couple of choices. I could say that the carbon on the left is carbon 5, or I could say that the one on the right is carbon 5. Sometimes you will be in a situation where you can identify 2 reasonable possibilities. I know you hate that ambiguity, but it is the universe in which we live. If there's 2 or more legitimate ways to identify isoprene units, and you've done it correctly, your answer is right. And so you have to trust me that I'm not going to give you 2 correct answers and make you choose the one that I happen to like at the moment to get the question right. You got it? Okay. So let's actually use limonene as an example. Let's just assume, for now, we'll choose the one on the left as carbon 5. We want to test whether that makes sense by seeing whether that carbon 5 is itself attached to carbon 1 of the next isoprene unit, because we know in the linear precursor, carbon 5 from the orange isoprene unit is attached to carbon 1 of the next one. Got it? I saw a hand. Yes?
Is there a reason that we should prefer one set of isoprene unit collections, or is it?
I will defer that question until we have a couple of alternatives, so it'll make sense to ask, to talk about it. Yeah. Okay, so let's just say then this is 1. Maybe I better switch colors to purple. Can you handle that mid-time? I know I can't either, so now we got to erase everything and make it orange. Except, watch this. Whoa. That took too much time, but there we go. Okay. So the question is, if we let this one be 5, does it make sense for this one to be 1? The answer is yes. It's right next to carbon 2 with the branching methyl group. That would make this one 4 and 5. So the first isoprene unit would be this one. The second would be this one. Then this would be one of the bonds between the 2 isoprene units. And then I would have another bond here. Now this is where I can start to learn some things, because the bond between orange 5 and purple 1 was present in this linear precursor, the thing that I told you, oops, that's an eraser, not a laser pointer. The thing that I told you was the precursor to all of these structures. That red bond there between orange 5 and purple 1 is also present here. So I don't actually have to worry about how that bond formed because it was present in the linear precursor. However, this bond between purple 5 and orange 4, that's not usually in the starting material. So if I were going to try to draw a mechanism for how limonene forms, I would need to account for this bond in blue that's not normally in the linear precursor. Does that make sense? So I'm using isoprene units to try to get a sense for if I were to draw a mechanism for what this molecule's formation is, what bonds do I not have to worry about versus what bonds do I need to worry about? Now, some of you are asking the question, what if, because I know you like to play the game what if, it helps you go to sleep at night. Is that what it is? Yeah, sure. The song from White Christmas about how when I'm worried and I can't sleep, instead of counting my blessings, I ask, what if? And then I can't sleep anymore, so it doesn't matter. All right, so let's just say this is, again, carbon 3, 2, 1. This is 4. Now let me choose the other direction. Let me say, supposedly, that, okay, maybe that's carbon 5. Does that make sense? Would that still work? Is that still rational? And the answer is yeah, because that could be carbon 1, and then this would be 4, and this would be 5. And then my concern would be, can I draw a mechanism? So the bond here between orange 5 and purple 1 would be the one that was already present in the linear precursor, and this new bond between orange 4 and purple 5 would be a bond that my mechanism would need to explain. And looking at both of these answers, I'm going to put this here in blood. They are both reasonable. So no, I'm not going to ask you, this is A and this is B, and if you choose one, good luck. No. Those are both reasonable hypotheses. And you could probably draw a mechanism for both that would use, you could draw a mechanism that would legitimately lead to limonene using both of these strategies, and it would be fine. Okay? So sometimes you're going to come up with more than one strategy for identifying isoprene units, as long as it makes sense to me. So the problem is that when you're in the test, something may temporarily make sense to you, but not actually make sense. So as long as your strategy correctly stitches isoprene units together with this pattern, both of these options are fine. Okay? Yeah? Sure. Could we have said here in the orange subunit that this was carbon 1 and the one with the double bond was carbon 3? Yes. Yep. And hopefully now you can see how we can get some of these, we can start to see structural similarities. We're not going to do menthol because it's basically the same as limonene in terms of its connectivity. Let's do alpha pinene, because I know that you're now starting to be okay with 6-membered rings, but 6-membered rings fused with other rings make the SpongeBob fires go off in your brain. So we want to work on that. One other hint that I'm going to tell you when looking at terpenes is look for the dimethyl head group. I told you that terpenes come from linear precursors that have heads and tails. The carbons 1, 2, and 3, this sort of dimethyl head group, that's always the end, or the head, I guess. That's always the beginning of the linear terpene. Sometimes you can find that dimethyl head group in your terpene product, and that gets you quite a ways towards understanding where the isoprene units are. So, where is the dimethyl head group in alpha pinene? Is that weird thing in the middle? The dashes there indicate that's going down below the page. And the reason the two methyl groups are splayed out to the side is it's really hard to draw things that are way below the page. We just mean there's an sp3 carbon there that's bonded to two methyl groups and these two carbons. So that is the dimethyl tail, or the dimethyl head group for the first orange isoprene unit. So we're going to go, that's 1, 2, and 3. Now we can identify the purple isoprene unit's methyl group there, and that's carbon 2. Now again, we're going to have a choice to make. We're going to need to choose which of these two is carbon 4. If I go here, that's 4, and then 4 would be, then where's 5, and how is that going to get attached to purple 2? So it's probably a better choice to go here for carbon 4. Notice the similarities between that and limonene. 1, 2, 3, 4, right? Now we're going to be in a similar situation. We could choose 5 here, orange 5 here to the right or to the left. It's not going to matter, but I will just pick one of them. 1, 2, 3, 4, 5. Does that make sense? Is 5 bonded to purple 1? Yeah, that looks pretty good. And this orange bond would be something that's present in the linear precursor. Then purple units 1, 2, 3, 4, and 5. Let's see, I need to write down the 4 and the 5. Now we can start to identify what new bonds we needed to make in pinene. This bond between purple 5 and orange 4. And then also this bond between purple 4 and orange 2. Now you can begin to see some of the structural similarities between alpha-pinene and limonene, even though they look so different. Look at the red bond between orange 5 and purple 1. That's the same in limonene as it is in alpha-pinene. Look at the blue bond between orange 4 and purple 5. That's the same. In fact, the only new thing here is this blue bond between orange 2 and purple 4. So probably you could make a mechanistic hypothesis. Probably alpha-pinene is structurally related to limonene, and probably you make something that looks like limonene first, and then you make alpha-pinene. You could hypothesize that and then go try to see how the organism actually makes the molecule. Now, we haven't done anything about mechanisms yet. We've just gotten good at, or we're trying to get good at, identifying isoprene units. Questions so far? Yes?
You said in that last one, the only new bond was the 4?
Was the one between orange 2 and purple 4. Yep. So you're going to see that these problems are related. Once you've solved the problem for how to make limonene, you're already most of the way to making alpha-pinene. And this is actually beautiful. Nature uses these similar pathways to generate quite diverse natural products. Yeah?
Listen, I'm just curious. I'm trying to figure out how geraniol, whatever you pronounce it, converts into menthol.
So it's geranyl pyrophosphate that converts into menthol. So for some of these, most of what we're going to be talking about is going to be how to get the carbons and the hydrogens in the right place. Sometimes getting an oxygen in the right place is going to be easy. We'll add water to a carbocation as an example. Other times there will be other enzymes that need to do that. I obviously am not going to expect you to invent an enzyme, so we'll sort of take it from with that sort of warning on what you'll be expected to do. Okay, others? Okay, I told you it would get worse before it gets better, so prepare yourself. What we're going to do now is we're going to look for isoprene units in what's called a sesquiterpene. Sesqua means 1.5 or 1.5. So a sesquicentennial celebration is a 150-year anniversary. A sesquiterpene is 1.5 terpenes. 1 terpene is 2 isoprene units. So how many isoprene units in a sesquiterpene? 3 or 15 carbons, right? So here's one from cedar trees. This one's called cedarol. And you are going to hate it so bad. 5-membered ring, methyl group. Another 5-membered ring, 2 methyl groups. This is where you're really going to hate. 6-membered ring branching off the 5-membered ring like that. Okay. Multiple fused rings. There's a 5-membered ring here, there's a 5-membered ring here, there's a 6-membered ring there. And then you can start counting the sizes of the other rings that you can form by continuing to go around the circle. A bridged tricyclic system is maybe what we would call this. So, the beautiful thing that OChem does to you is first it freaks you out, and then as you take a breath and focus on what you know, you start to see order emerge from the despairing chaos. Which is actually a theme in the gospel, light versus darkness. Jehovah slaying Leviathan, the chaos monster. That's now your connection to the gospel. So spiritually inspiring, right? Yes. Anyway, you'll look at this, and the first thing you want to do is focus on the methyl groups. Look for the branching methyls. So we're just going to label them in gray because we're not sure where the beginning is. The methyl groups are all carbon 3, and the carbons directly attached to the methyl groups are all carbon 2. So after I look for the branching methyl groups, my next task is to see, is there a dimethyl head group? Is there a carbon with 2 methyl groups on it? Yep, right there. Okay, great. So that's my head group. We'll let that be orange. And again, what I'm going to be doing is comparing the structure of this really complicated sesquiterpene to its linear precursor, which should be 3 isoprene units all linked together in head to tail fashion like this. So I'm going to abbreviate the pyrophosphate group like that just to save us time. This is called farnesyl pyrophosphate, and it is the linear precursor to cedarol. Here are the isoprene units in farnesyl pyrophosphate. There's orange, there's purple, and then I guess we'll choose green. And you see these bonds between carbon 5 of one isoprene unit and carbon 1 of the next isoprene unit together in head to tail fashion. So our task is just to identify the correct connectivity. As before with limonene, there's a chance that we're going to come up with multiple hypotheses. As long as your hypothesis involves reasonable 5-to-1 linkages between isoprene units, you're probably right. Or your answer is indistinguishable from the right answer, meaning you'd get full credit, okay? So we got a choice here, starting with the orange head group, 1, 2, 3. We got to choose where 4 is. Should it be here, or should it be here? You want to go left. Why don't you want to go up? Because we don't usually see 4 adjacent to 2, or just because it sort of feels better. Let's just see how your instincts go. Here's the thing, on these problems, I know you want an algorithm that allows you to make steps forward and be confident at every step along the way that you were making the right choice. But seriously, folks, when has your life actually been like that? You often have to take, more spiritual inspiration here, you often have to take a few steps into the darkness, not knowing beforehand the things which you should do, and see whether it works out. So, sure, let's go with your instincts. Let's call that one 4. Now, I think it's pretty clear that this one should be called 5. Why? because then that gets you in the right place to have this be carbon 1 of the next isoprene unit. That makes this one 4. Okay, what now? Where am I going to go now? If I go here and this is 5, would it make sense to make this one 1, 2, 3? If I go here and this is 5, would that make sense to go 1, 2, 3? Yeah, so that's one of these cases where it's actually indistinguishable. You can come up with a reasonable hypothesis either way. So let's just choose. I don't know. Okay, I heard you say up, so there we go. 1, and then this 1, 2, 3, 4, and 5. And I'll use highlighting now to highlight the individual isoprene units. I think we've identified some other alternatives along the way, some other possibilities. Suppose I asked you a question in which I identified the isoprene units for you, but I didn't label the bonds between the isoprene units with lovely colors. They were just there. And suppose I asked you this question. Of bonds A, B, C, D, and E, which were present in the linear precursor? Okay, which were present? It's not hard if you can count, because the ones that are between 5 and 1 are the ones that are in the linear precursor. So we'll use red 5 to 1 and red 5 to 1. So that's only A and C. In blue, we'll choose all the other bonds that were not in the linear precursor, and those would be the ones your mechanism would have to explain. Now again, I'm not asking you to draw a mechanism for the formation of cedarol. You could do that. I actually have it in my notes, but I think we'll start smaller than that. Did you get the idea? I could also ask the question, which of these were not in the linear precursor? Okay, yes? Yeah, the linear precursor is just as many isoprene units as you need, 5 to 1. Yep. And your body and nature makes these first and then does the chemistry. Okay, so now that we've gotten decently good at identifying isoprene units and the linkages between them, we need to learn a little bit about the types of chemistry that happen with isoprene units. And in making these molecules. We're going to start with the simplest linear precursors. You've seen one that was 10 carbons, that's geranyl pyrophosphate, but we need to talk about where geranyl pyrophosphate comes from, and it comes from these 2 precursors. Again, I'm going to abbreviate the pyrophosphate group like this. This one is called dimethylallyl pyrophosphate, and this one is an isomer. In this one, the double bond is between carbons 1 and 2 rather than between carbons 2 and 4. Okay? And I'm going to continue to use the colors orange and purple because if we compare these 2 precursors, this one is called isopentenyl pyrophosphate, or IPP. You can, if you look at this linear precursor, geranyl pyrophosphate, the way we've colored the isoprene units is going to be consistent. The orange portion of geranyl pyrophosphate comes from dimethylallyl pyrophosphate, and the purple portion of geranyl pyrophosphate comes from the purple isopentenyl pyrophosphate. Okay? So, we're going to illustrate how this happens. And the answer is basically a small alphabet of reactions. So I'm going to list them and we'll show them in making geranyl pyrophosphate, and then we'll need some other examples along the way. All right, so step one is leaving group leaves. That's sort of an SN1 or E1 style first step. We're going to use dimethyl allyl pyrophosphate for that. Why? Because the good leaving group is at the allyl carbon. So when it leaves, that gives you a resonance stabilized carbocation. This is not revolutionary, this is not groundbreaking. In fact, it's somewhat boring. This is 351 type chemistry. Do you see how that carbocation is resonance stabilized? Got it? Okay. Notice now it's electrophilic. It's electrophilic at both carbons 5 and 2, okay, which is interesting. Now let's go step 2. Step 2 is pi bond attacks the carbocation, and there's an important element of regioselectivity that we need to deal with. So once you make that carbocation, I'm going to just use this resonance structure, then the pi bond from isopentenyl pyrophosphate acts as a nucleophile. This is an addition to alkenes type reaction. You have seen this in 351. All the time you had pi bond attacks an electrophile, and you've not seen really a pi bond attack a carbocation in 351, but the principle's the same. Recall that when having a pi bond attack an electrophile, the central issue was who gets the new bond and who gets the positive charge. And you remember there was a principle there. Who should get it? Should we make the new bond with purple 2 or purple 1? Why? So that 2, the more substituted carbon, can have the positive charge where it's more stable. Because you remember that more substituted carbons, more substituted carbocations are more stable. Because alkyl groups are electron donating. So we'll show the pi electrons from the bond between purple 1 and 2 attack carbon 5 to make a new bond between purple 1 and orange 5. That new bond we will illustrate here in red. And that's how we make that head to tail bond in the linear precursor for all of these terpenes. It's simple alkene addition type chemistry. Now, I'm not done yet because I have a positive charge on carbon 1. Look at where I want to get with geranyl pyrophosphate. Can you think of a reaction that you did in 351 that would allow us to have a pi bond in the right place?
Have a base take a hydrogen off carbon 4.
A base remove a proton from carbon 4. Okay, so third type of reaction step is elimination of a beta proton from a carbocationic intermediate. That's like the second step of E1. So yeah, we will take this carbocation, protons that are adjacent to carbocations are acidic. Now some of you are going to ask, aren't there beta protons on carbon 1 and on carbon 3? Why don't they get removed? Why do instead we get the pi bond between 2 and 4? And the answer is the enzyme must control the regioselectivity. At least you could argue that if the pi bond goes here, it's a tri-substituted alkene, whereas this would be a di-substituted alkene, and more substituted alkenes are more stable. But there's no difference in substitution if the pi bond goes over here. Nevertheless, nature wants the pi bond to be between 2 and 4 because that sets us up to have an allylic leaving group, which we could use to do a next set of reactions to elongate another isoprene unit. So a base removes the beta proton. We don't care what the base is, perhaps some group in the enzyme active site, puts the new pi bond there, and then that gives us our geranyl pyrophosphate product. Now, hopefully you can see how this process could be iterative. How I could, if I wanted to, now geranyl pyrophosphate itself has an allylic leaving group, and how I could go on to have that leaving group leave, giving me a positively charged resonance stabilized carbocation, and then have another nucleophile attack. I could elongate to 3 isoprene units, or 4, or 5, or so on. Okay, yes?
Well, it seems to me like in the first step, the resonance structure, it seems to me the second resonance is more stable.
So the question is that when this resonance stabilized carbocation, you have positive charge shared between carbons 5 and 2, these are not 2 different carbocations, they are 2 incomplete pictures of the same carbocation. So technically it's not correct to say this one is more stable than this one.
I'm just saying, like in terms of production, product.
You are asking, does the nucleophile attack on carbon 5 versus carbon 2? Preferentially, it appears to attack on carbon 5, at least in the synthesis of geranyl pyrophosphate. Presumably, that must be enzyme controlled. I know you don't like that answer, but that's probably what it is. It must be enzyme controlled. Okay. All right, now we've got the linear precursor. We need to see a couple other steps. Generally, these 3 steps describe most of the possibilities. The other thing you need to know is beware of carbocation rearrangement. Sometimes 1,2 hydride or 1,2 methyl or 1,2 alkyl shifts are necessary to get the right connectivity in the end. So let's do this with some of the terpenes. We're going to get started. We will hopefully get to limonene. We will probably need to do alpha pinene next time, but this will be enough to get going. So your precursor for limonene is geranyl pyrophosphate. Okay, and I just want to copy the structure of limonene down so you can have an idea of where we need to get. And it might actually be useful for me to redraw geranyl pyrophosphate in a slightly different orientation. Okay, and we'll label the atoms. And you'll see that at least in thinking about the mechanism, we've already done a lot of the heavy lifting just by numbering the atoms and by identifying bonds that were present in the linear precursor versus not present in the linear precursor. So do you see how this is just another view of geranyl pyrophosphate? I've just rotated around a carbon-carbon bond. Another important thing is alkene stereochemistry in the linear precursor. These were, well actually, there is no stereochemistry around this alkene because it's both of them are methyl groups. But here, this is an E double bond, and that stays that way. Now, if you look at limonene, we need to have a bond, make a blue bond between carbons 4 and 5, right? We got a problem. As it is, carbon 5 isn't anywhere near carbon 4. It's actually on the wrong side. We would actually prefer the other stereoisomer, the Z isomer, where carbon 5 would be down here instead of this hydrogen. Okay? So let me show you how nature takes care of that. First, we'll do step 1, which is leaving group leaves. And that gives us this carbocationic intermediate. Now, what I'm going to show you, I always get questions about, and the question starts with, but why can't you? Okay? So I'm going to tell you ahead of time, why can't you? Remember, I told you that the problem with the geranyl pyrophosphate precursor was that carbon 5 is in the wrong place. We really want the Z stereoisomer where the carbon would be down here. Some people look at this resonance stabilized carbocationic intermediate. They draw the other resonance structure, which I will do here. They say, lo and behold, the bond between carbons 2 and 4 is now a sigma bond. Therefore, I can rotate around it to put carbon 5 in the right place. That sounds good, doesn't it? But it turns out that's not what nature actually does. Why does that not work? Is the bond between 2 and 4 a sigma bond?
No.
Is it a full double bond? No, it's somewhere intermediate, right? Conjugation involves lining up of p orbitals on carbons 2, 4, and 5 to create an extended pi system. If you rotate around the sigma bond, you break conjugation, and suddenly what was a resonance stabilized carbocation is a less stable carbocation. So it turns out you can't really rotate that efficiently. Nature knows this. So watch what nature does. This is kind of cool. That pyrophosphate leaving group is still around. Now it's a 4- group. We'll show it with just one lone pair. Notice that the resonance stabilized carbocation is both, the positive charges simultaneously on carbons 2 and 5. If we attack on carbon 5, we just go back to the previous step, and that's probably happening. But if we attack at carbon 2, we generate an intermediate that looks like this, in which now we do have a full sigma, completely sigma bond between carbons, purple carbons 2 and 4, and then it's free, we are free to rotate around that carbon-carbon bond. So this intermediate has a name. It's called neryl pyrophosphate to distinguish it from geranyl pyrophosphate. Now we can do the rotation around the carbon-carbon bond that will allow us to get to a conformation where carbon 5 is in the right place. As soon as that happens, that pyrophosphate group's coming right back off. We'll go right back to a carbocation, but now it has the right shape. Yeah? Is that with the enzyme? Yeah. Okay, so we're not quite there, but these 3 or 4 steps that I've shown you for what terpenes do are sufficient preparation for the exam. So, good luck to you. I have office hours on Wednesday, and I'll see you in class on Wednesday.